Okay, so the next differentiation rule is the product rule, and it states this. This involves the product of two differentiable functions. Let u and v be two differentiable functions of the variable x. Then their product uv is also differentiable. And let me write it there. The derivative of uv is equal to u times the derivative of v plus v times the derivative of u. Okay, so let's now prove this. We straight away start with this expression. This expression means this derivative, which by definition is a limit, you already know. We have so this is going to be the difference quotient for the function uv and the limit of that difference quotient. So the difference quotient is u of x plus h times v of x plus h. This is the value of the product uv at the input x plus h minus u of x times v of x divided by h. Now to figure out what this limit can possibly be, we introduce a term because we will have to write a somewhat long expression, so I have written 1 over h first times u of x plus h times v of x plus h. So what we are going to do here is that we will write the term minus u of x plus h times v of x, but then to balance it, we also write the positive counterpart of it. And of course, we originally had minus u of x times v of x. Okay, so this trick, which often is applied when dealing with limits, even has a name. It's called the middleman trick. We introduce something in the middle of a calculation out of nowhere like this, so that it cancels out. If you think of it in that way, if you try to go back from this step, then you of course get that, because it's actually not there. If you think of both the terms at once, then the net effect is 0. There is no net effect. But introduction of these two new terms, now it will give us something. We will now arrange things somewhat cleverly, you see that if you think of this term with this term, then there is a common factor which is u of x plus h. So we can write 1 over h times u of x plus h times v of x plus h minus v of x. Minus v of x, like this. Whereas the last two terms have the common factor v of x. So for that, what we can do, we can take v of x outside and write those two terms like this. U of x plus h minus u of x times v of x. Now if you also consider this 1 over h and bring it inside this expression, you can write this entire thing like this. U of x plus h minus, so it's outside, okay. So u of x plus h will stay just like that. Let me in fact write this a little more towards the left so that I have space for what I want to write. So this is u of x plus h times v of x plus h minus v of x divided by h. Okay. So this can be thought of as a single term. Similarly, plus u of x plus h minus u of x divided by h times v of x. Okay. Now you see, we don't really know at this stage if this limit, this is after all a limit, no? If this limit exists or not, that we don't really know that. In fact, that's what we want to show. So, looking at this, we now have to figure out whether this limit exists. So, we stop the calculation here itself, and now we have to say some things. Namely, what are we given? We are given that u and v are differentiable functions. Since u and v are differentiable, so these two limits exist. One of them is, of course, the derivative of u with respect to x, which is this limit, u of x plus h minus u of x divided by h. And the other limit, let me write it here, is this. V of x plus h minus v of x divided by h, both of these limits exist. And something else is also true. Also, note that this difference quotient is handled by this limit, by the existence of this limit. This one is handled by the existence of that upper limit. Upper limit means the one above this. But there is a term v of x multiplied with this. That, however, is in fact a constant with respect to the variable h, because x and h are independent of each other. As h is approaching 0, x is just x is not changing. So, you can treat this term as a function whose limit exists times a constant. So, obviously, this product also has a limit and is equal to v of x times the limit of this. However, what will you do with this term, u of x plus h? The term it comes with can be handled by this limit, but this, unlike this one, is in fact dependent on h. So this is where you need to recall a fact about differentiable functions, namely that every differentiable function is also continuous. So that's what we have to use here. Also, since u is differentiable and hence continuous, the limit of u of x plus h as h approaches 0 is simply u of x. And that is why we can now further continue this calculation and write this entire thing like this. Hence, but we recall where we started all the things, namely here. So this now becomes, we are going to look at this and write the things above. So this becomes equal to, or we have already written equal to. Let me first write the limits, then I will write their values times v of x plus h minus v of x divided by h plus limit, well, because we have already recognized the fact that v of x is constant with respect to h, so you can just simply bring it outside of the limiting process. And write like this: minus u of x divided by h. So, actually what we have done is that we have, after this step, this is what we are writing. And what is our justification for doing so? The justification are the various limit laws for functions that we have already come across. For example, the limit of this exists, and so does the limit of this. And in fact, this is u of x. It exists after all. And that is why the product of these two functions also has a limit, which by one of the limit laws is the product of the limits. Similarly, Here you see a function whose limit exists and it's multiplied by an expression which is constant with respect to the variable age. And that's why the limit of this product also exists and is equal to that constant times the limit of the function. And because these two functions, this product and this product, both have limits, so their sum also has limit and is equal to the sum of the limits. And that is why this is equal to this. So now if you see what you have got here, if you write now the expressions values, whatever we may call them, of these limits, this one is u of x. U of x means I can just simply write u. Okay, that it's understood that it's the value of u at x times the limit of this, which is what? dv dx plus v of x means you can just write v and du dx. So that's how you get the product rule. This is the proof of the product rule. In prime notation, recall that this is not the only way to write the derivative of a function. We can also write, in place of du dx, we can write u prime. So that's the prime notation. In prime notation, the product rule looks like this. The product rule is this. The derivative of uv is equal to u times the derivative of v plus v times the derivative of u. The product rule helps us with many situations. Let's see an example that will illustrate this rule and why we need it. And that example is, actually we are going to see two examples. The first one is example 7. 7 means, because we have already seen other examples before, so this is the 7th one. Find the derivative of this function y equal to, so it's a product of two polynomials. One of them is x square plus 1 and the other one is x cube plus 3. It's not mentioned by using the product rule or without using the product rule. It's up to us to decide. So let us first see what we get if we apply the product rule. So we straight away just write the derivative. We have, and we also mention by the product rule this. So what does the product rule say? See, a very easy way to remember the rule is this. You differentiate one of the two factors at a time, and this you do to both the factors. You keep one of them as it is and differentiate the other. You keep u, simply u, and you differentiate v. Then you keep v intact and differentiate u. That's all. So say we keep this one unchanged here. So we have to then multiply it with the derivative of the other factor plus, then we keep x cube plus 3 as it is and multiply it with the derivative of this. Okay, now we have to recall how to calculate these derivatives, which we already know. Okay, we have to use the sum rule, the power rule, the constant rule, all these things we have to do, but we won't do so in great detail. We will just write the derivatives straight away. So you know that the derivative of x cube plus 3 is the derivative of x cube plus the derivative of 3. The differentiation process distributes itself over a sum to all the terms. And this property of the derivative operation is called linearity. Actually, there is another thing also which comes under this name linearity. It's just a name, okay? Do not try to think too much about it. It's called linearity. Actually, it's the sum rule, but the sum rule and the constant multiple rule. What does the sum rule tell us? The sum rule tells us that if we have a sum of not just two functions but finitely many functions, then differentiating the sum just means you differentiate each term. That's the sum rule or its general form. And the constant multiple rule tells us that if your function is multiplied by a constant, that constant can be taken outside. These two things together are called linearity of the derivative operation or operator. Why is it called linearity? Let's just leave that thing, okay? It's just something that I am just telling you. You will see later on why it's called linearity. What it has to do with being linear in some sense. Right now, however, let's see what the derivative is. The derivative of x cube is, you know what to do. The exponent comes down and then it gets reduced by 1 plus 0. Some people won't write 0 here, but it's better to write at this stage. It shows that you know what you are doing. Plus x cube plus 3 times what's the derivative of x square? The exponent comes down and then gets reduced by 1. So 2x and 1 has derivative 0. So we get this 3x square times x square plus 1 plus 2x times x cube plus 3. Now let's see, let's just multiply the terms out and write a single polynomial. What shall we get? 3x to the power 4 plus 3x square plus 2x to the power 4 plus 6x. That means this will be 5x to the power 4 plus 3x square plus 6x. Say someone does not want to use the product rule. In this case, that's possible. In this case, that's possible. Then what one has to do, this is the alternate solution. One just has to multiply these two polynomials and get a single polynomial and then differentiate that polynomial. Are we going to get the same thing? We should. Let's see. So if you multiply the two, I have to write derivative. Let me write at once. Instead of first figuring out what y will be, let me straight away write dy dx. So if I multiply the things, x squared times x cube is x to the power 5 plus, see, I am going to get x cube because I have to multiply x cube and 1. But I will also get 3x squared plus 1 times 3 is 3. So if I now differentiate this using sum rule, power rule, constant multiple rule, all those things, what shall I get? First I will differentiate x to the power 5. So the exponent 5 comes down and then gets reduced by 1. Similarly, here I am going to get 3x squared plus, I am doing the things very fast. Actually, there are many intermediate steps. First of all, you have to write this equal to the derivative of this plus the derivative of this plus derivative of this plus derivative of this. Then the derivative of this is this. That of x cube is 3x squared. But then the derivative of 3x squared cannot be, it can be written at once, but it involves another thing, which is the constant multiple rule. The coefficient 3 comes outside, and you have to write 3 times the derivative of x squared. X squared has derivative 2x, and 3 times 2x is 6x. And of course, 3 is constant, so you get 0. Are we getting the same thing? See, 5x to the power 4 plus 3x squared plus 6x. Yes. Now, you can see that in this case, not using the product rule gives us a shorter solution. This is not always the case. Okay, in some cases, using the product rule will give you a solution more quickly. It's up to you to decide which one you want to use. But sometimes there is no option other than using the product rule. And the next example is about that. We have to use the product rule. What type of situation can it be where we just have to use the product rule? Let's see. So the next one is example 8. Here the functions are not given directly. Let y is equal to y be equal to uv, where u and v are functions of some variable x. So we don't really know. We are not given what u and v are exactly. They are some functions and y is their product. But some information is in fact given about them. Find the derivative of y at the point 2 if the value of u at 2 is equal to 3. We are not given what the function u is entirely, but it's given that its value at 2 is 3. Also, it's given that the value of the derivative of u at 2 is -4. Next, the value of v at 2 is 1. And finally, v has derivative and its value at 2 is equal to 2. With all these things given, can we find the derivative of y at 2? Yes, we can, and in this case we have to use the product rule. Since the functions u and v are kind of not entirely known, so product rule is the only way. We have by the product rule y prime at 2 equal to, so y is uv, that means it will be u times v prime, but because we are calculating it at 2, so u of 2 times v prime at 2 plus v of 2 times u prime at 2. Okay. So u of 2 is what? 3 times v prime of 2 is 2 plus what is v of 2? 1 times u prime of 2 is minus 4. So 6 minus 4, this is equal to 2. You will encounter this type of conditions when you solve initial value problems, some differential equations with some given conditions. Okay, they are going to come at some point, we will see what they are. There you will encounter this type of conditions. So in spite of not knowing what the functions u and v are fully, we still can calculate the derivative of their product at a given point if enough information is given to us. Okay, so next comes another rule, rule 6, and this is the quotient rule. Okay, so instead of product, if we have a quotient of two functions, can we, and both of them are differentiable, then can we differentiate the quotient? Is it also differentiable? If so, what its derivative is that we are going to see in the quotient rule. Okay, so let's first see what the rule states. Let u and v be two differentiable functions of x where v does not vanish, v is never 0. Then the function u divided by v, the quotient u over v, is also differentiable. And this formula you need to remember, it's not as easy to remember as the product formula. It has an asymmetry. The product formula has a symmetry. U times v prime plus v times u prime. Whatever you do with u in one term, you do an exact similar thing with v in the other term. Here, however, because the original thing itself is asymmetric about u and v, u is the numerator, v is the denominator. This is not a symmetric situation. So the derivative formula is also asymmetric, and it is this. U divided by v turns out to be turns out to have v square in the denominator. It's also a quotient itself. And in the numerator, you have v times du dx minus u times dv dx. The numerator has a form that is somewhat like the product rule. However, there is a minus in between. It's a difference, not a sum. I mean, at least how it looks like. It's a difference and not a sum. And also, the first thing that we keep intact is the denominator. I mean, the denominator function v comes first. You multiply that with the derivative of u minus, then you keep u intact and differentiate v. Okay, so the entire thing is asymmetrical. Always remember it like this, that the denominator has square of the denominator of the original function. And then you write v first, the denominator comes and it doesn't change here, times the derivative of u minus u times the derivative of v. Now, once you write this term, where v is intact and you are differentiating u, the other term you know what to do. Then you keep u intact and differentiate v, but there is a minus in between. Alright, so let's now prove this one. So, like the product rule, we straight away go for this. We have, and you do of course understand the necessity of this, because otherwise the quotient will be meaningless. So we have ddx of u divided by v. So by definition, it is this limit. Okay, this time we have to be extra careful because the given function itself is a quotient. U of x plus h divided by v of x plus h minus u of x divided by v of x divided by h. So this is the value of the function at the input x plus h, and this is the value of the function, entire function, at the input x. Okay, so now let's do a little algebra. And now the denominator will gather some more terms than simply h. V of x plus h times v of x, and the numerator is going to be u of x plus h times v of x minus this times this, v of x plus h times u of x. Okay. Now here also we have to apply that middleman trick that I was talking about when proving the product rule. Because we have to write a somewhat long expression, this time also let's write this separately. So we write 1 over h times v of x plus h times v of x. So what are we going to introduce this time? Times v of x. So this time we simply introduce u of x times v of x. That's it. That's what we introduce. Plus minus v of x plus h times u of x. A question may come to your mind, how do we know what we should introduce? These, of course, are just some standard proofs in which if you see the proofs once, you know what the proof has done and you can memorize what term you have to introduce in your middleman trick. But say you encounter a similar situation elsewhere, which is different from the proofs. There also say you need some middle term. How would you know what to introduce? Well, you have to keep in mind what your aim is, what type of terms you expect to have. And if you think about this thing, you kind of do a back calculation where say you think of this and then try to go back and see what ultimately you get. So thinking forward and sometimes also backwards, and you try to merge those two things, that will give you an idea of what you need here. It may sound very complicated at first, but if you keep thinking about this, at one point it will click. Okay, but now how can we arrange the things? Let's see. First of all, of course, whatever we have here within the square brackets, let's just take common terms out and write the thing. We just keep this term outside as it is without thinking anything of it for now. And here, from the first two terms, we can take Vx common out. And we can write u of x plus h minus u of x times v of x. Okay. Plus. But you see, the ultimate formula, the form in which we need the derivative, that has a minus. So why not take instead of taking, what is the common term this time? It is u of x, but instead of taking simply u of x common out, in order to bring a minus, let me take minus u of x outside. And when you do so, you will also see that then the other factor is again in the form that you want, v of x plus h minus v of x. And now we bring in that outside term in the calculation inside and arrange things. You will see that there are some cancellations. For example, when you write this divided by this, you are of course going to write this divided by this minus this divided by this. In that first term, v of x divided by v of x is 1. And that's why you will be left with what? U of x plus h minus u of x. Below it, say I write simply h. Okay. And with that, I write that other term which survives, which is 1 over v of x plus h. All right. So that's the first term. Then minus. This time what will happen? Here, however, we do not have any cancellation. So we are going to write u of x divided by, so two things we have to write, v of x plus h and v of x. Whereas with this difference, we are going to write h in the denominator, because do not forget that besides this and this we also had h. Alright, now we have to stop the calculation here and answer what happens to these quantities when h approaches 0. Do they individually have limits, just like before? If so, can they be combined using the limit laws to calculate this limit? And if so, what will be the final expression? Since u and v are differentiable. Sometimes when we go through such proofs, say you go through a proof and you write the proof on paper for practice, for understanding, you've encountered that, you see that some situations are similar. So you may have to write the same thing again. So don't be lazy, write it, okay? Don't be lazy and write something like this. Since u and v are differentiable, we have a situation like the previous proof. Now, when you write a formal proof, please write it fully. At least not be lazy in writing these things, in not writing these things. Okay, so since u and v are differentiable, the limits minus u of x divided by h and exist. Okay, but they are not the only limits we have to deal with. We also have other terms. What about them? We have this and we also have this. Well, in these terms, it's only the v of x plus h that depends on h. U of x and v of x do not change with h because they do not have h. And just like before, this time we are going to use the fact that v is continuous because it is differentiable. Also, since v is differentiable and hence continuous, the limit of v of x plus h as h approaches 0 will exist and will be equal to v of x. Hence, now we can use the limit laws like the previous proof and write what this will be. Since I do not have space anywhere else, I have to write it here. So after this and this, we are going to continue this thing and write hence limit h approaches 0, u of x plus h minus u of x divided by h times limit h approaches 0, 1 over v of x plus h minus limit, don't want to waste this space, so I am just writing like this, limit of u of x divided by v of x plus h times v of x times limit h tends to 0, the difference quotient for v divided by h. If you are wondering what will happen when you write v of x here, will there be any problem because it's in the denominator, but there won't be any problem because v of x is not 0 for any x. v never becomes 0, that was already given in the statement. That's why using the limit laws, do you remember which of the limit laws we are using here? See, this is given and v is never 0, and that's why by the quotient rule of the limit laws, this limit also exists and will be equal to 1 divided by v of x. In a similar manner, this limit will be equal to u of x divided by v of x times v of x. And what are we using here? We are using the constant multiple rule of limits, where this function is multiplied by this constant u of x divided by v of x, which is constant with respect to h. It doesn't have h, so it doesn't change with h. And the other limits, of course, are derivatives. So now we can write the final thing. So this will be what? This is going to be du dx times 1 over vx. Well, I can simply write v because we want the final answer in that form. So I just simply write v minus the limit of this, as I said just now, is u divided by v times v times the limit of that difference quotient, which is dv dx. Okay. That means here we are getting 1 over v, if I write this first, times du dx minus u over v square times dv dx. Now if I take v square in the denominator, then this becomes v times du dx minus, since we already have v square here, we will simply have u dv dx. So that's how you get the quotient rule. Now let's also see how the quotient rule looks in the prime notation. So you see that these derivatives of products and quotients of differentiable functions need continuity of these functions also in their proofs. in the prime notation, the quotient rule is this. V square V dot u prime minus u dot p prime. The prime notation looks nice, but it doesn't show the independent variable, and sometimes it can be confusing. Okay. Now let's see an example illustrating the use of the quotient rule. Unlike the product rule, which sometimes you can just simply not use because you can calculate the product, quotients are more difficult to deal with. Find the derivative of y equal to t square minus 1 divided by t square plus 1. You see, ideally we should write find the derivative of this with respect to t, because t is the independent variable. But because only one function is there and only one independent variable is there, so it's usually omitted. It's understood that we have to differentiate with respect to t. But when you go to multivariate calculus, which is there in this book, at some stage we are going to get to that, there you have more than one independent variable, and there you cannot make such statements, differentiate this function with respect to which variable you have to mention. And there you, as a result, encounter partial derivatives. Here, however, there is only one t, so we have to differentiate with respect to t. We have by the quotient rule this dy dt, don't write x this time. So what should you do first? You write the square of the denominator in the denominator. Then the numerator has the denominator first of all unchanged times the derivative of the numerator, the other thing, t square minus 1, and then t square minus 1 remains unchanged and you differentiate the other thing, t square plus 1. T square plus 1. If you differentiate t square, you are going to get 2t. Differentiating 1 gives you 0. So this time we won't write it. Minus t square minus 1 times. Similarly, this one is also 2t plus 0 divided by the square of t square plus 1. Now we will simplify a little bit. In fact, it's quite easy here because you have a common term, 2t. So you can take it common out. Two t times t square plus 1 minus of t square minus 1 means minus t square plus 1. when we do calculation in school, when we are in lower standards, when we are introduced to algebra, to keep track of the terms that you are cancelling, we usually strike them out. Say we have a calculation which looks like this. Then what you do this and write 3. You get rid of this habit now. Okay, now you do not need to keep track of things like this. You have done it enough number of times. So here don't strike this t and t square and minus t square. Simply write 2t times 2. In fact, if you see your book, do you see any such marks, any such flashes in the book? No, because that's just for our own understanding. And at some stage, when we have seen these things enough, we should just stop using this. So that means our final expression is this. Okay, so that's the example. After this, there are a few other things that we will see in the next calculus video. So I'm just ending things here itself for tonight, and tomorrow we have our usual linear algebra. And since we have already completed the section on nilpotent transformations, the next one I think is the rational canonical form. So we will see tomorrow what it is. So that's just it, folks. So see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.